Okay, welcome again to this section, right? So last week we talked about Starknet, layer 2s, and SNARK and STARK, the differences between them. We also sent out assessments via email. I believe like a lot of you received that. And definitely we'll send out the one for this week, like within the week as well. And we'll definitely review the assessment like before the end of the class, right? So but then today we'll be going deep. We'll be discussing zero knowledge proof. We're talking about account abstraction. We'll be going in depth in SNARK and STARK. And as well, we'll talk about validity proof. So Gospel, good to have you teach these topics.
Excited. Yeah. Can you hear me?
Yes, we can hear you.
Okay, cool. So let me quickly just go ahead. Yeah. So welcome everyone. Good evening, good morning, good afternoon, depending on where you're joining from. It's really good to have you guys here, and I hope you have fun during this class. I hope you're able to get something out of this class. So here's how it will work. I want it to be an interactive class, right? I want you can always drop a message in the chat or even unmute yourself and speak. I don't mind, right? As I'm going, you can just unmute yourself and draw me back. I'll do my best to answer your questions. Or if you don't want to say anything, you can just drop a message in the chat. I'll be coming to check the chat once in a while because I'll be sharing my screen. Yeah, let me quickly share my screen right now and we'll go from there. Can you see my screen?
Yeah.
Yes.
Cool. So once again, good to have you guys here. I'm excited for this class because zero knowledge proofs, validity proof, account abstraction are things I really find interesting, and I'm really happy to share it with you guys. And I hope at the end of this, you guys probably like it a bit more than you already do. Yeah. So we'll be talking about zero knowledge proofs. We'll be talking about validity proofs. We'll be talking about account abstractions. And if you don't have any idea of all these things, don't worry. I'll do my best to simplify it in the best way possible, in a way that if you've not heard it before, you'd probably be able to pick it up and understand something, right? And also note that there will be a lot of oversimplification, which I believe will be a foundation for you to learn more things, right? Because I would not want to complicate things, so I'll oversimplify things, but understand that those oversimplifications are the fundamental ideas you need to understand to learn these things, right? Because today we are definitely not going to do anything, let's say complex or mathematics and stuff like that. But then we are going to be able to give you a very good fundamental to be able to learn these things on your own, or even give you a path to follow, right? So let's just go ahead. I wouldn't want to share this Zoom in because I would do some demos later. So I just want to leave it this way. That's why I'm not just doing it in this slideshow way. So don't mind my tabs. I keep a lot of tabs. This one's not even, today is a good day. That's why the tabs are like this. So yeah, let's go. So we're talking about zero knowledge proofs, STARK versus STARK, like the differences, validity proofs, and a very basic introduction to account abstraction. So, so what are zero knowledge proofs, right? So this is just the typical Wikipedia definition. So it says zero knowledge proofs can be defined as follows. In cryptography, a zero knowledge proof or zero knowledge protocol is the method by which one party, the prover, can prove to another party that the given statement is true, while the prover avoids conveying any additional information apart from the fact that the statement is indeed true. The essence of zero knowledge proof is that it's trivial to prove one possesses knowledge of certain information by simply revealing it. The challenge is to prove such possession without revealing information or additional information. So I know this is, I just said now, actually very boring because it's Wikipedia, like it's Wikipedia. So we know the kind of definitions they give, but don't worry, I'll definitely explain this. But this is just the formal definition based on Wikipedia. But then over the course of this slide, I would break these things down in a way that you'll be able to understand. So yeah, just a quick history, right? So this is meant to be a deep dive of ZKP, right? So zero knowledge proof. So just in case. So I just did just a short form. So yeah, this was the notion of zero knowledge proof was first proposed in 1980s by MIT researchers. So just history stuff, right? But then let's come to the interesting part of this. So what problems do ZKP solve, right? Now, when I hear these kind of things, I want to ask myself some questions. So first off, why do I need to reveal critical information in order to convince another party, right? So for instance, why do I need to give you more than necessary or even more information than you're supposed to know? For instance, why do I need to show you the amount of money in my account for you to know that I have money? Or why do I need to show you my bank balance, right, before I can buy things in a store? Like for instance, now if you go into ShopRite, right, you just put your card, right? You don't need to show them your balance, right? And this is just an hypothetical, that's not ZKP, don't get me wrong, that's just something that you can relate to, right? So another question is, what if both the prover and the verifier cannot be trusted? So this is another problem ZKP solves. So in zero knowledge proof, there's a protocol, right? Actually, like this is in the core, right? You know, you can see some preliminary, like for instance, now, if you want to explain things, we build up, right? So maybe at the basic level, when we are just trying to make sense of these things, having some weaker protocols. When I say protocol, I mean ZKP protocols. You might have scenarios whereby you have to trust the prover and the verifier, but at the core, you're not trusting anybody. The prover is not trusting the verifier, and the verifier is not trusting the prover. We just need to have a proof, right? So now the question is, what if both the prover and the verifier cannot be trusted? So what if you as a prover, you trying to prove something to someone else, they don't trust you. Even the verifier, they don't trust you. We just need something that is independent of the prover and the verifier. We just need to say, okay, this is this. And we want to be able to prove to the verifier, who we don't trust, that this thing we're trying to prove is right, right? So what it says is that there is a protocol, so to say, that will help us make these claims without trusting both the prover and the verifier. Right. So the next question is it necessary for the verifier verifying party or the verifier to acquire more information apart from the fact that the statement is true? Is it safe for the verifier to acquire more information rather than the validity of the statement? Right. The same question. Why do I need to give you more information? Do I need to give you more information? Is there a way for us to do it in a way that I don't need to give you more information, which is best, right? So as I move forward, please, like I said, if you have any questions, just unmute yourself and speak, or just drop a message in the chat. Okay, let me quickly check the chat. Okay, cool. So let's now come down a bit to the real world, right? What are the possible applications of ZKP? See the word possible, because some of these things are proposed, some of these things are already existing, but just generally, right? For instance, now, let's take the first one, proving statement on private data. If you're a developer or a backend engineer, and if you've ever built an authentication system, like a login system, a way to log into websites and all, you would find out that here's how it works, right? You come into a website, you put in your password is hashed using a hashing algorithm. When it's hashed, it's stored in the database, right? So your main password is not stored in the database. Then when you come back and you want to log in, what happens is that they hash your password, the one you imputed on the front end, and they try to compare it with the one already existing in the database, right? So this is how a traditional web system works, a traditional login system works. Now, this looks like ZKP, right? this looks like ZKP, or this is maybe the closest explanation to ZKP for in the traditional system. But note, this is not zero knowledge proof because somehow we are seeing the password because the password is being sent from the client to the server. But then this is something like, we can use this as a very close example. This is not ZKP. ZKP is more secure than this. We don't even need to know your password in the first place, right? But this is something that looks like ZKP, right? So basically, I give you my password. You don't see my password. You see a hash. And in the database, I compare these hashes and I validate if you're the right user. After you log in, I don't have your password, but I just know that you came in somehow, right? So just take, for instance, imagine that you were meant to, let's say, okay, let's go in the like Western world, and maybe people that use like credit scores and all those kind of things. They don't need to have those things. Like, they don't need to have those particular information to be able to validate that these are the kind of things that you would be able to access. For instance, now they don't need to start asking you, okay, this is your card PIN or this is your credit score, but they just know that a platform has aggregated these things to a single dashboard and it says this person is eligible for this service or this person is eligible to get these benefits, right? They don't need to actually say that this is what your score is, right? So basically, the whole idea behind ZK, zero knowledge proof, is that I want to be able to prove something to you, but I don't want to give you extra information. No extra information. So from the name, you see zero, you see proof, right? Zero knowledge proof, right? So zero knowledge, meaning that I'm not giving you any information. I'm not giving you any new information apart from the fact that what I'm telling you is true or false. So if I'm telling you that this thing is red, and I don't need to tell you more than that, but I just need to come up with a protocol, so to say, to show you that this thing is actually red, right? So now there's this very good example I like using, which is, how do you convince a colorblind person that two balls of the same structure, the same texture, the same physical, the same physical or the same feel of different colors? Now remember, someone who can't differentiate colors will see both of them as black, right? So how do you convince this person that these two balls are of different colors? Now see this like this popular way of doing it. So basically, you tell the person that, okay, these are two balls, which person say, okay, this is these two balls are both black, right? And then you want to prove to the person that these two balls are of different colors without actually telling the person the color, because to an extent, the person will not believe you because he's seeing the ball and he's saying that these two balls are black. So in this case, you don't even need to you don't need to give person more information. You just need to convince the person, because from what he or she is saying, it's saying that these two balls are black, right? Now, you tell the person that take these two balls, put it at your back and keep switching them, right? But then if I'm able to differentiate these two balls, then the colorblind person is able to say that, okay, it seems this person knows something. And the more times that I am getting these balls, the more the confidence of this person is increasing. For instance, now, let's just say we're using percentage, right? And let's say we are trying to try this thing 100 times, right? So if the person switches the ball at the back and I find it once, it's like 1/100, right? So 1% confidence, right? If the person switches it again, I find it again. Before you know it, we have done it like 50 times, and the person is saying, okay, yeah, I think this person really knows that these two balls are different, because how am I switching these balls and this guy or this girl is still getting this thing right, right? So basically, you have been able to prove to this person that these two balls are of different colors without actually giving any extra information about these balls. Now, what I just explained now is interactive. We are going back and forth, but you know, this won't really be applicable to computers, you understand, but we'll get to that, right? So let's go back to this thing. So I've talked about proving statement on private data, which is your bank statement, your bank account. We don't need to know your bank account. We don't need to know your bank statement, right? We just need to know that you are eligible for this benefit. Okay, let's say something similar is you want to apply for something that is limited to a particular country, right? So I don't need to know your country. I just need to see like maybe an aggregated dashboard that says that you are eligible. So maybe a logic or a program on the back end, I've already done computations and said, okay, this person is eligible. So the person staying at the counter would not need to ask me my country. You just need to see, okay, this is this person's this platform says that this person is eligible. Note that this is not ZKP. This is just something that looks like ZKP or something that is similar, but it's not ZKP. It's just a way of trying to make it make sense. So something else, anonymous payments, which we know, for instance, you've seen some, I don't know if you've been in the blockchain space for a while, you must have heard of Tornado Cash. So this is actually a reward application. In Tornado Cash, you can send money, you can send tokens without people being able to track your address, right? It's just like you sending token anonymously, right? So this is a perfect example for anonymous payment. So it's already happening, right? You can make payments, you can transfer, and even if you go into a task scan and try to see all the transactions, you won't be able to say that this is the person that sent it, right? So that is then the last one, which is kind of the most important. I was meant to actually put asterisks on this. Oh, sorry. I was meant to put asterisks on this because outsourcing computation. Now, this is, most of these things, these three now, most of them are actually under privacy, right? They're under privacy, proving statement on private data, anonymous authorization, anonymous payment, they're under privacy. But outsourcing computation is another part where ZKP is really used, which is under the umbrella of scalability, right? So basically, these first three examples are under privacy, right? But this fourth one is under scalability. So basically, this answers the question, how do I compute so that the next party don't need to compute, right? So how do I run this program so that the next party don't need to run this program? The next party is just supposed to be able to confirm that I've actually run it without trusting me. So basically, you are telling me that, hey guy, I've run this program, this is the output, you don't need to run it again. And without trusting you, I'm able to prove, so I'm able to just run the protocol, which is me being on the verifier end, and say that, hey, this program is true, right? This program is true, this program is correct, I don't need to verify any other thing. And this is the core fundamental of the whole idea of zero knowledge proofs and Cairo and the whole thing, right? It's basically building programs that we don't need to run multiple times. Okay, let me just contrast this so that it will make more sense. On the Ethereum blockchain, if you send a transaction, it gets to the mempool. When it gets to the mempool, miners, or okay, not miners now, because it's now a proof of stake blockchain. So people that validators would go into the mempool and pick up these transactions and try to validate them or try to run them, right? And now for every person who wants to do the same thing, the person will have to run it. So basically, if let's just say there were 100 people on the blockchain, which is not true because there are more, but let's just say there are 100 people on the blockchain, and then for me to add the particular transaction to my database, because it's more like it's just like a distributed database. Everybody has their own copy, and at the end, the goal of everybody is to be in sync, right? Everybody's trying to be in sync with the other person. That's why it's a peer-to-peer network. So I'm trying to make sure that my data is the same thing as your data and all. So basically, what's happening is that every single person is trying to make sure that their own data is in sync with the other person's data or the other person's database, right? So what they are doing is that they're running that same transaction just to be in sync, right? So basically now there's something here that you have to understand is that they are running these transactions, and these transactions is deterministic, right? It's deterministic, but for them to be able to confirm that this is real, they need to run it, which that it takes a lot. Like, why do I have to run a program when you've already run it and you're sure? But then that's just the way it is, right? But then ZKP is telling you that, okay, let me run it once, and you'll be able to verify that I've already run the program and this is the output without trusting me. You don't need to trust me, you don't need to know me, you just need to know that I've run this program and this is an algorithm. This is a set of process, or this is a set of rules that you would need to run for you to be able to confirm that I've actually done what I said I've done without trusting me. You don't need to know me, you just need to know that if I run this protocol, I'm able to verify that this person has done this computation without any form of trust, right? So this is really something you should think about, or this is something you should think about when you're learning about Cairo, is that this is the whole idea of Cairo. So Cairo is meant to be a program or a like a programming language whereby when you run it, you are able to create proofs, and then you're able to verify the outcome of these programs without having to run it again. But you can, if that's too complex, you can just leave that for now and go ahead. So let me just stop here a bit. So does anyone have any question? Please go ahead and ask. There's no stupid questions. Or if you even have questions from the last class, you can just chip in. I will just try to answer it. You can just ask before I go ahead.
So I have a question.
Cool. Go ahead.
So say I'm a user and for some type of computation that a different person is gonna like run, right? I have like some task. I'm like, okay, I'm gonna send it through. So will I have to like generate my own proof to like maybe verify that, you know, the computation was done correctly, or is the proof going to be sent to me?
Okay, so very good question, because you know, I said something at the beginning. I'll be oversimplifying things for our understanding, but now let me bring this down a bit. So basically, what happens is that Cairo is supposed to be a language that it's more like it abstracts all the whole like proving and all those things for you. So basically, when you compile a Cairo program, it's being sent to a prover, then the prover verifies it, or the prover creates a proof, then it sends it to the verifier, and the verifier does the whole thing. But now the only thing you have to bother about is to write the program, right? It's more like proving for all, or general knowledge proof for all. You just need to write the program. You don't really need to bother about what's happening at the end, but just know that that thing happening at the end is what gives you the ability to scale. Because now the reason why it's called a layer 2, or the reason why, or the goal of layer 2s, is that they want to be able to solve the problem of scalability, right? So basically, when they do it that way, they're able to use less gas, they're able to use less computation while doing similar to what people are doing on the Ethereum blockchain, which is just running programs and running transactions, right? So basically, you don't need to know all these things, or you don't need to bother about that. It's just like as a smart contract developer, you will not start bothering about what's happening on the, like, what miners are doing or what nodes are doing. You just need to write your smart contract, just like it is here. You just need to write your Cairo program, deploy it on chain, and when anybody tries to run a transaction, all these things happen at the back. But what you know is that you are having a verifiable source of truth, which is the data coming out of it, because on the back end, all these things are running for you.
So how can I like be sure, like if I cannot like maybe compute that stuff myself, like how can I trust a different party? Like how can I trust this magical backend is gonna verify and send me through things
I guess
without really involving me, you know? So and you know.
So you know, in everything you do, it depends on where you are, right, or your level of knowledge. So now there are some people that actually insist on wanting to prove these things themselves and their tools. So there's something called SHARP, which is a shared prover. So basically, it's part of the whole architecture. But then, if you don't want to use it, which is like this, if you don't want to use it, like most people, because most people don't want to bother about this, right? Because they are like white papers, they are like documentations that says that this is how it's done. But then if you really want to be sure, then yes, you can dive deeper and try reading about shared provers and how these things work under the hood, which definitely at the end you get your answer, because yeah, it's actually good to want to verify these things, but then it takes a bit of it's more technical than just writing Cairo program. But then if you want to verify, there are ways to verify these things to the last. Even there, like you can just you know, it's an L2. So if you go to the Ethereum blockchain, you see a contract that is meant to be a way to verify states and all those kind of things. So basically, yes, you can do that yourself. But then what I'm saying is like, I'm trying to, this is like most people don't want to do this, right? Most people don't want to do it themselves. They just want to run programs and get output and all. So yeah.
Thank you.
Yeah, welcome. Cool. So does any other person have any question before I go ahead? Okay, I would assume that. But remember, please, you can drop your message in the chat and I will do my best to answer. So quickly, I want to just do something really, I'll be quick. But then it's just something to prove that, just like we are now going a bit deeper. So this is a bit of will I call this mathematics, or let's just call it practical? Let me not call it mathematics. So basically, this is just a popular problem, right? It's called a graph tree coloring problem. Basically, what it's saying is that you should construct this graph or construct this shape you're seeing here with all these circles in a way that there will be no 2 points connecting each other of the same color, right? So if you look at this graph, you would see that you would not see any one whereby you have 2 of the same color connecting each other. So this is just the problem you're trying to solve. And this might look easy to do, but when you have a lot of points, you'll find out that this is actually a problem, right? A very big problem. But then this is a very good way to explain how zero knowledge proofs works. Now, here is the whole idea, right? I meet a contractor, or I meet a person that draws graphs. Don't mind me, people. But then I meet a person that like draws graph for a living. In quote, I'm just using that as an instance. I'm telling the person that I want you to draw this kind of graph for me, but like I want you to draw this graph for me to look like this. But then the person now tells me that if you see everything, or if you see all the points in this graph completely, you might decide not to pay me, right? Basically, so it's saying that if I just draw it and give you, you might just decide not to pay me and go and draw what you've already seen, right? So it's basically saying that I cannot trust you. So what I'm going to do is that I'm going to show you just 2 points at every iteration. So basically, it's telling you that once it's done, he will not show you the full program, or will not show you the full shape. He will just show you 2 at a time. But then how it's supposed to work is that the more he shows you at random, your confidence level increases. Now, you know, when I talked about the problem with colorblind person trying to prove something, I talked about confidence, right? So basically, if I tell the person to do this thing for me, but the person does not trust me, right? So the person is saying that if I'm going to show you this thing, I'm going to show you step by step. I'm going to show you just 2 points. And I'll keep spinning it and trying to randomize it so that you will not find out everything. But then I'll just be showing you 2 points at a time. So basically, I'll show you these points, just these 2 points, and I'll show you these 2 points, just randomly, right? So there's a program like that, like, so here is it. So this link is in the slide. So later you can go and check it out. So basically, can you all see this this website I'm on?
Yeah.
Yes, we can see.
Cool. So now we generate the graph, right? So basically everything is all black, right? So basically now you see this thing called here, it's sitting here, it's called confidence, right? So the more I find, the more the confidence increases, right? So this is the confidence level, which is now 0%, right? But then the more I find connections that are of different colors, the confidence increases. Then until I find one that is not of the same color, my confidence will kind of go down a bit. But then now there's something interesting. In zero knowledge proofs, it's not really about getting it perfectly. It's about being able to convince you to a very high level. For instance, now 90% confidence is good, right? For instance, like it depends on how confident you want to be able to say, to be able to pay this contractor that is doing this thing. So basically, you might say, I need to be 60% confident to pay you, right? So even if you find at the 65% that this thing did not work, then that is when we'll not start having issues, right? So basically, this small, like for instance, when I said 90%, that 10% is inconsequential or is negligible in the grand scheme of things. For instance, now imagine that you have 1 million points, right? And you are not finding like 5 points or 10 points or even 100 points that are wrong. 100 points is negligible when it comes to 1 million points. So since it's at random, you can say that that particular small failure or that small error would be inconsequential in the grand scheme of things, right? So I'll show you. So let's just play this game quickly. So this different colors, my confidence has increased. I tried this again, my confidence has increased. I tried this again, my confidence has increased. I tried this, my confidence is increasing. I tried this again. So they are random. Even if I come back here and try to show it again, they are coming out at random. So now my confidence at 44%. So let's try and find one that will give us error, and let's see. Right. So it will be very hard because as I'm revealing these things, they're kind of randomizing the graph. So as I'm trying it again, it's giving me something different. I'm trying again, giving me something different. See, now my confidence is at 58%. So this is actually very, very high, right? So 60%, 62%, 64%, and in fact, I might go up to 100 and I'll not even find another one that is actually wrong. So basically, this is a good, would I say this is a good proof? But then there's something here that you can just do everything quickly, but then you will not find. So let me just do this. If you click on Turbo, you see that this will just go very quick. So let me just click on Turbo. You see it's actually doing everything itself, and it's increasing. Now it found two of the same color, right? It found two of the same color, but now it's already at 93%. So I can decide to forfeit this and say that, okay, this thing is like, it's inconsequential, it's negligible to what I'm doing, right? It's negligible to what I'm looking for. I might say, okay, let's just leave this, right? You've proven to me, if you can give me this up to 93%, then I'm sure that you know what you're doing, right? So let's try it again. Again, it's doing it at random and 80%, right? Even to show you how random this thing is, even when it's doing it in itself, it's hard, it takes a while for it to find this, right? So this is just a way to understand ZKP. So as I do this thing, my confidence level increases until I find one. So these things are random, right? So I'll drop this link on this link is on the slide. You can go back there and play with it and maybe read all these things here. And it's actually fun if you want to try and play with it. So this is the link here, the demo here. So let's go to the next one, which is okay. So at this point, does anybody have any question? I'd love to take questions. If you have questions, and just, or does anyone not understand the graph, the game I just played now? I can see explain that if you want. Okay, cool. So now, we've been talking about proof since, right? We're talking about ZKP, but then there's something that we've been like one theme around what we've been doing is like all these things are interactive. Like even this thing I just did now, I need to interact with this graph, right? I need to interact with them step by step, the first, the second, and all, right? But then if you want to scale this for using a computer, you would know that we cannot be doing back and forth, right? A computer is not a human being that will be discussing and say this one, that one, this one, that one. So basically, how do we create proofs that is more like prove once, verify millions of times, right? So how do we create those kind of proofs? Because these ones we've been talking about since are more like when we create, would give you verify back and forth, back and forth. It's not like you can't do back and forth in computers or in programs like this, but it's not really scalable if it was that way, right? So basically, we are trying to say, how do we create zero-knowledge proofs that we don't need to go back and forth? We just need to prove once, at least in most cases, prove once and verify millions of times, so to say. So basically, like I said here, ZKPs don't require back and ZKPs that don't require back and forth interaction. So unlike interactive proofs, non-interactive proofs require only one round of communication between participants and prover and verifier. The prover passes the secret information to a specific algorithm, to special algorithm, to complete the zero-knowledge proof. The proof is sent to the verifier who checks that the prover knows the secret information using another algorithm. So basically, it's more like, hey, guy, I know that this is this, and this is my proof. Hands off. Verify it 1 million times, I don't care, but I've given you my proof, right? And I'm sure because of the zero-knowledge proof algorithm is, if the zero-knowledge proof algorithm is correct, then I should be very sure that you always get the right answer, or when you're trying to verify what I gave you, it will always be true, right? And also note that even this thing I'm talking about being negligible and all, in the grand scheme of things, you are dealing with millions and millions of numbers, so you'd probably not even find any scenario whereby you have false. Like, you know, when I showed you the graph ordering problem, you saw that sometimes it was giving false, right? But then because of in the real world or in the real zero-knowledge protocols, you're using millions and millions of numbers to the extent that you would not find a case whereby this thing is giving wrong responses. You would not find any, because maybe when you have billions and billions of numbers, maybe 3 or 2, which you know that you have to, maybe you probably use a quantum computer to be able to even get the slightest false value out of these whole values, right? So basically, like I said, the ZK snaps and ZK stacks are the main examples. I think Kelvin already touched a bit on this last week, but we'll just quickly would talk about them more today. So there are two main types of, there are others, but there are two main types of non-interactive zero knowledge proofs. So basically, ZK snacks is basically means zero knowledge sourcing non-interactive argument of knowledge, right? So we know this one, which is zero knowledge. We know the meaning of zero knowledge. Non-interactive, we just talked about it. You don't need to go back and forth. Argument of knowledge is basically the proof or the statement or how you, is basically knowledge, right? So basically, argument of knowledge means, let's say what I'm trying to prove, right? But then the word succinct might be new here, which is, it just basically means that they produce proofs of smaller size and they can be verified quickly, right? So basically, because when you're talking about computers, you're talking about information, you would have to take size and space into consideration and time. You understand the time complexity of these things, right? So it's very, very important, because if you really want to scale, you need to take into consideration how long these things take. You understand how long these things will take, how much these things can take, right? So basically, that's why this whole idea of being succinct is very, very important when it comes to zero knowledge proofs, right? So this is how ZK SNARK work. Like I said, I'll oversimplify things, because under the hood, these things are actually built on the foundation of beautiful mathematics. And if you say you want to go into that, I want you to go into that on your own. But if you say you want to go into that now, all of us will be confused, including me, because it takes a while, and it takes maybe your personal story to understand. But then know that on a very high level, a ZK SNARK uses something called the common reference string, right? And this common reference string is public, right? It's public, everybody can see it. So we can say that, okay, this is the common reference string used for proving this computation. So that if you want to run it again, you can run it again, right? If you want to rerun, because this common reference string is important for you to even verify, right? So it's public, right? But for you to be able to generate this public parameter called the common reference string, you need to generate it. Like you need to use some, like, let's say, secret source of entropy. So let me just read this out. So generating the public parameter is a sensitive operation, because it's importance in the protocol. It's important in the protocol security. If the entropy, which is mean the randomness, using generating the common reference string, gets into the hands of a dishonest prover, they can compute false proofs, right? So basically, in as much as the common reference string is public, the process being used to create this common reference string should not be public. It should be very, very private, right? It should be very private, because once the wrong person gets your entropy or your source of randomness or the random value used to generate this common reference string, there'll be a problem. Now, a way to solve this problem is using something called multi-party computation. From the word multi-party means many people computing. So basically, we have a couple of people coming together to do computation, so that even if you want to start looking for this randomness, you have to go and meet all of them. Now, at the end of this, you see why this is actually unique. So basically, multi-party computation basically means we have a couple of people, and instead of just one person generating the common reference string, we have a lot of people generating it, so that at the end, it will be hard to, even if you find one, you have to find a lot of them for you to be able to trick this system or compute false proofs, right? So when I mean compute false proofs, basically means to be able to create proofs that are wrong. It's more like, I know that something is false, but I'll just compute it the way I like, because I have this source of randomness, and then start giving wrong values, right? So that's why this multi-party computation is important. So basically, it says it's used in reducing the risks of generating public parameters, right? Public parties participate in the trusted setup ceremony, where each person contributes random values to generate the common reference string, as long as one honest party destroys their portion of the entropy, the ZK SNARK retains computational soundness. So what does this mean? So imagine that 100 people come together, which in most cases they are much more than 100, right? 100 people come together to do this multi-party computation. Remember, like I said, this multi-party computation has to do with people coming together to, let's say, contribute randomness, if that's the best word to use. They are contributing randomness to make the value more random or harder to find, right? So basically, now what they are telling in this last line is that as long as one honest party destroys their portion of the entropy, the ZK SNARK protocol retains computational soundness, meaning that if we are 100 and 99 decide to compromise, if one person disposes their portion of the entropy, you can't find it. So basically, you need to get everybody. If you feel like you want to get this thing, you are really if you are committed in trying to break this whole protocol, you need to get every single person, right? So basically, if out of 100, one is honest, we just need one honest person to dispose their entropy, which we'll talk about later because it's called toxic waste, right? So it's called toxic waste. So disposing this is waste, right? In as much as it's in the computer and computational sense, it's actually waste, right? So as long as one honest party destroys a portion of the entropy, the ZK SNARK protocol retains computational soundness, meaning that everyone is meant to destroy it, right? But they're telling that even if everybody decides not to destroy theirs, and just one person destroy their own, it means that it will retain computational soundness, meaning that what they want, ideally, every single person should dispose that, which we'll talk about later, which is called toxic waste. So when you dispose these things, it's called toxic waste, right? Don't look at it in kind of waste in real life because that would actually confuse you, but that's the best way to see it. So then lastly, you have, if you want to really, I think someone talked about SECOM. So SECOM is a domain-specific language for building circuits. So when you talk about circuits, you're talking about zero knowledge ZK SNARK, right? So SECOM is for building circuits. It's a domain-specific language, meaning that it has its own syntax. It's not under any language. It's on its own. It might look like some languages. In fact, actually, it looks weird. It doesn't look like a lot of languages, but you can quickly just write SECOM on Google and you can just quickly read up on what it does. Then you have Bellman. Bellman is a crate, which is like you can, if you're coming from Python background, you might say a library or an SDK, depending. But basically, Bellman is a crate in Rust for building SNARK programs, right? So you can just, I'll share this slide after this call, so you can just quickly check these things out. Yeah. So, okay, our time is fast spent. So let me just quickly. So yeah, ZK SNARK is actually more like ZK stacks is actually more like ZK SNARKs, but with some kind of modifications, right? Or some kind of improvements. So basically it means zero knowledge, scalable, transparent argument of knowledge. So they didn't put non-interactive, but it is non-interactive. You understand? They didn't put succinct, but it's actually succinct, right? But then it produces proof of large sizes. So basically, what it's saying is that the sizes for proofs created by ZK stacks, they are larger than the ones created by ZK SNARKs. But there's a catch somewhere, and you see it later. It is not literally like this, but there's a catch somewhere that even makes it, because this is what Cairo is being built upon, right? There's a catch somewhere that would make you understand why Cairo is even like why they are using ZK SNARKs for something that's producing proofs of large size. You get to understand that later in this slide. So let's explain scalable quickly. So ZK stack is faster than ZK at generating and verifying proof when the size of the secret is large. So when I mean secret, it's basically what you're trying to prove, right? So what you're trying to hide. You understand? You might call it witness. You might call it witness. I just change it to secret because you understand it that way. But then this is also called witness in the ZK world, right? So the secret is called a witness. So basically, they're telling you that it is faster at generating and verifying proof when the size of the secret is larger. Take note of that, when it's larger. So basically, maybe if you want to compute something very, very small, you might say, okay, let me use ZK SNARK. But when you're talking about big things like programs, like imagine you have a Cairo program of like 2,000 lines, right? This is actually large, right? So it's more like when it's larger, ZK stack is better. But when you want to do small things or things that are not very large, ZK SNARK is better. But we'll still get to the differences. But just want to point this out why they are saying it's scalable, because it's more like it's counterintuitive if you hear that okay, it produces large sizes and also it's fast. You're like, how? how would something that is large be giving you faster proofs, right? So also it is transparent in the sense that, you know, we talked about trusted setup. We talked about trusted setup, which is a way to generate the common reference string, like I said, for ZK snacks. But now they're not telling you that ZK snack is transparent, meaning that they don't go through all those processes, because now you had a trusted setup, right? A trusted setup, in as much as this is ZKP, when you hear a trusted setup, so those individuals participating in that trusted setup ceremony are actually trusted, right? So it's not the typical idea of trust, which is it will be easier. Like, it's not the typical idea of trust, but just know that this is a trusted set of people or trusted set of computers, depending on how you want to see it. But basically, a trusted setup has to do with a group of computers coming together, which you know that is being controlled by humans, definitely, but coming together to generate these proofs, right? Also, sorry, generate this common reference string. So basically, they are saying that ZK-SNARK relies on publicly verifiable randomness to generate public parameters for proving and verification instead of trusted setup. So basically, they're telling you that, okay, we also have public parameters like common reference string, but then we don't use trusted setup ceremony. We use a public verifiable source of randomness. So they use hashing, right? They hash values and you can see it publicly. Nobody has to do trusted setup ceremony and all those kind of things. So that's just one of the differences. But then let's just go to differences main. So now, let's just quickly go over this. So with stack proofs, prover and verification times only slightly increase as the witness, which is the secret, grows. So, you know, I said something at the beginning, when I talked about larger proof sizes. So it's more like, for instance, now, if you're doing things that are little, right? If you're a developer, or, you know, have an idea about data structures and algorithm, you understand there's something called big O notation, right? There's something O of n, meaning that it increases linearly, right? O of n square, meaning that it increases in a quadratic manner, right? But then if something increases linearly, it means that if the number of, like, n, let's just say O of n, please, if you don't understand it, don't worry. But then O of n, if O of n increases, that means it will increase linearly. So if it was 2 and it took X amount of time, when it becomes 4, it will take 2x amount of time. When it becomes 8, it will take 4x. When it becomes 16, it will take 8x, and so on and so on. So it's actually increasing linearly. But they are telling you that stack proofs don't increase linearly. It might be generating large proofs, but it doesn't, instead of doing 2 times, instead of going from 2x to 4x, it might go from 2x to 2.5, 2.5 to 3.5, 3.5 to 4, instead of doubling by 2, right? So basically now it's suited for big proof, because when we start scaling, we would need something that don't increase as we move. Because imagine that you now have 1 million, and when n is 1 million, you're now having 2 times 1 million. But then ZK Stack is telling you that, okay, we are not going to give you 1 million. We're going to give you something like 500,000. We're going to give you something like 400,000, right? So what it says is that ZK Stacks don't increase linearly. It increases at a more, it increases at a less exponential rate, right? So if you get me, so basically it doesn't increase as ZK Snacks increases slowly, and it builds up, which makes it more scalable, because we might be doing something minute and it might not really show, but then when it becomes really large, you appreciate the scalability of ZK Stacks, right? Then, like I said before, stacks are more transparent because they don't use trusted setup, right? ZK Stacks produce larger proofs than ZK Stack, meaning that they generally have higher verification overheads. However, there are cases such as proving larger data sets where ZK Stacks are more cost effective. Like I just finished explaining. When you have smaller, you might have what we call higher verification overheads. But then when it comes to really large data sets, you appreciate ZK Stack because it will scale with you. It will scale based on just what it's saying. It will scale in a more cost-effective manner, right? So ZK Snacks are more widely used compared to Stack because yes, ZK Snacks was created before or was introduced before ZK Snacks. So yeah, right now you would easily get started writing ZK Stacks program, sorry, ZK SNARKs program than you do for Stacks, because it has been existing a couple of years before ZK Stacks came into play. I know I'm mixing these things, but hopefully you understand me. I'm mixing these things. But then Stacks, when you talk about Stacks, you're talking about ZK Stacks. When you're talking about SNARK, you're talking about ZK SNARKs. So like lastly, ZK Stacks doesn't produce toxic waste. Like I said, when ZK SNARKs, they generate those things and dispose their entropy, dispose their source of randomness. This creates toxic waste, right? But now ZK Stacks, they're telling you that we don't do that, right? We don't use trusted setup ceremonies. We use hashing, right? So using hashing, we don't need to throw anything away. We just know that we didn't even create any toxic waste in the first place. We don't need to throw anything away. We are using hashing, and hashing is something hashing is, you may know about hashing, right? It's just converting something to another thing, and you're not able to get like from input to output, but you can't go from output to input. It's a one-way function, it's a one-way thing, right? So I know I've said a lot. At this junction, please ask your questions before I know our time is already fast spent, but just ask question before I quickly go over the last couple of things we have. Okay, does anyone have any question? So does that mean everybody's understanding? I'll be really happy. But then you can go ahead and ask your questions, please. Okay. If no one has, let's just quickly wrap up, and maybe at the end someone asks. I hope so. I hope someone asks a question at the end. So basically, we are going to the second to the last thing we have here, which is validity proofs, right? So basically, for you to understand validity proofs, you have to understand its counterparts, or basically, it will help you understand it better if you understand its counterpart, which is fraud proofs, right? So just know that these two ideas, validity proof, fraud proofs, they have to do with roll-ups, which Kelvin talked about last week, which is, sorry, the last class. The roll-ups are layer 2s that basically what they do from the name roll-up, right? So basically, instead of adding transactions one by one, they roll up the transactions and create something smaller, and they add it to the Ethereum blockchain. So instead of you add 10 transactions, they combine it into something small and add it, so that at the end they are charging something lesser than what you would normally get on Ethereum blockchain, right? So but then validity proofs are mechanisms to add it to the Ethereum blockchain, because when you say something is building on something, right, there needs to be a way for this thing building on that thing to sync, right? So basically, these validity proofs and fraud proofs are ways that L2s sync with L1, right? So basically, I'm saying, okay, I'm an L2. After doing all my magic, roll up, everything, how do I now sync with the Ethereum blockchain? How do I sync with a layer 1, another layer 1, right? So let's explain fraud proof. Then we'll now explain validity proof. So what are fraud proofs? So fraud proofs are an optimistic way of adding to the blockchain. So it's more like, let me just use a very typical example. So imagine that we are all invited, or we all bought a ticket to a party, right? Or to an occasion. And we get to the entrance, and they tell us that you can walk in. We don't need to check that you paid or not. You can walk in. But at any point in time, if someone at the entrance suspects that maybe he doesn't like your movement, and he's noticing that this person might be trying to trick us, right? So they are being optimistic. So they are assuming that everybody's being honest, you understand? So they're assuming that everybody entering this occasion will be honest, right? But then if someone at the entrance, maybe part of the bouncers or something, now sees and say, okay, I don't trust this person's movements, let's check this person, right? So that way it comes in, right? So the way optimistic proof work is that you keep adding transactions, but at any point in time, someone can say, I want to dispute this. I want to say that, I want to prove that this person is not right? I want to prove that this person is trying to do something wrong. I want to prove that this person is trying to add a transaction that is not correct, right? So basically, that's how it works. They add transaction, but at any point, there are a set of people that are in charge of looking for these things and say, okay, this is this transaction. I want to dispute this transaction. let's have like an interaction, because the way it works is that once someone finds your transaction and says that this transaction is fraudulent or this transaction is fake, then you guys will start an interaction, so to say. You guys will start having this back and forth, and okay, maybe you create a proof, you bring it back, they verify, and at the end, if they find that you are wrong, you are being penalized because some part of your tokens are going to be taken, or basically you're going to be penalized. Maybe if your tokens are not taken, maybe you're going to be removed, depending on how it's been implemented on the particular rollup. But I think this is how it's done, an optimistic rollup. If you're found wanting, if someone disputes your transaction and they are able to confirm that you're actually wrong, you're actually trying to do something wrong, you'll be penalized, right? But this has some benefits, right? This has some benefits. But then one of the disadvantages of this is that you would have to wait a while. It's called dispute time delay, right? You have to wait a while before, because for instance now, if these things are happening per second, there will be no way to actually track these things, right? So you cannot be sending transactions per second and you are saying that nobody who would actually find out that you're adding something wrong. So there needs to be a time limit that someone can come and dispute. Because if it was per second, then it would probably be faulty, because if you're adding transaction every second, then how would the person that even wants to come and do anything even find you, right? So it happens, there's a time limit. So it's more like during this time, I can come and dispute your transaction. But if after this time, nobody comes to dispute this transaction, then we believe you are fine, right? So there's a time delay, So, but then this is it's cheaper, right? Because like hypothetically, it's cheaper because we believe that since it's not happening every time, since the dispute is not happening every time, it's kind of cheaper, right? But then now let's go to validity proof. Validity proof is that we are taking a pessimistic approach. We don't trust anybody. We don't trust you. You must create a validity proof to prove that your transaction is valid. That's where the name comes from. Like you must create something that says that we don't want to trust you. We believe that everybody is trying to do something wrong, which is the pessimistic approach, right? We are saying that give us a ZK proof, or give us a proof that will tell us that you are right. So we don't even need to dispute anything. If your proof says you're right, you're right. If your proof says you're wrong, you're wrong. We don't need to. In fact, if it says you're wrong, you can never add it in the first place, right? So basically, validity proof takes the approach, the pessimistic approach, saying that we don't trust anybody. Give us a proof. We don't want to be optimistic about anything. We just believe that anybody can be anything, right? So this is how validity proofs work, right? So it's a mechanism whereby you create proofs and try to add them to the L1. And when you try to add them to the L1 has a verifier. If the L1 can verify what you sent, no problem. But if it cannot verify, it is not allowed, right? But then on the other hand, fraud proofs take an optimistic approach. You send it in. Then if anybody decides to dispute, they dispute, and you guys start going back and forth, right? So validity proof is generally faster because now you just have to create proofs and go. If it's possible to add it, to add. If it's not possible, but then optimistic approach, you need to kind of give them a time limit so that someone can come and dispute, right? So I think I guess I've explained everything here just while I'm talking. So let's go to the last one. Account abstraction, which is something very, very interesting, right? It is not it's not related to zero knowledge proofs and all those stuff, but it's actually a very unique concept, right? And now for you to understand account abstraction to an extent, okay, someone asked a question. Let me quickly check that. Since the prover is supposed to be powerful and is different from having miners carrying transaction out, does it mean that there won't be MEV on Starknet? Very interesting question. Now, in as much as, so, okay, first off, right now, the only people, like they're called sequencers, right? So basically the way you have miners, they are sequencers on Starknet, which is you send transactions, the seeds, and try to create proofs for your transaction, right? So basically, it's more like you create a Cairo program, you run it, and then they see it, and they create proof for it and send it to the verifier and all. Now, but then, yes, in the future, there will be a mempool because it will be public. But right now, the only sequencer, to the best of my knowledge, the only sequencer is being run by Starkware. So definitely right now, there will be no MEVs, right? But then in the future, yes, if it's public, then apart from MEVs, there will probably be, MEV is a very big concept. There are many ways to do MEV. So definitely you see parties coming in to try out these things and try to extract value. But right now, there are no MEV because of the only sequencers are Starknet themselves. And yeah, so I hope that answers your question. This is a very good question, actually. Account abstraction, like I said, for you to understand account abstraction, you need to understand how it normally works, right? So quickly, on the Ethereum blockchain, there are contract accounts and their contract accounts and their externally owned accounts, right? So basically, externally owned accounts are the normal accounts we know, right? You say, for instance, if you want me to send you token, you just send me your address, right? That's your externally owned account, right? You just send me your address, I'll send you token and all those kind of things. Like for the most part, what you can do with that account is basically to sign transactions, right? To sign transactions and to sign messages. Apart from those two things, natively, there are not a lot of things. In fact, right now I can't think of any other thing you can do with your account. Maybe there's something I'm forgetting, but what I know is that you can only sign a message, which is like signing a message and generating signatures, or signing transactions themselves, right? So these are the two things that you can do using a normal account, right? But then an account abstraction is telling you that why are EOA so rigid? Why don't we just create something that is not really tied to just having being able to sign transaction and all those kind of things, right? Or why do I have to store, or rather, why do I have to write down 12 word seed phrase or 24 word seed phrase and all those kind of things, right? So basically, they are telling account abstraction is just a way to make accounts more abstract, more flexible. So when you talk about abstraction, just for the word, you would understand that abstraction is a way of not just being on the foundation, creating something on top of what's already existing, right? Creating something that would abstract a lot of the whole jargons, a lot of the whole technical things that are happening under the hood, right? It will take you above what it's currently giving you and give you something that is a bit easier to use, right? Abstraction is like mainly about making things easier, making things more flexible. You understand? So, like I said here, abstraction is simply a way of making blockchain account more flexible, thereby allowing for endless possibilities for use of accounts on chain, right? In fact, the possibility you get using account abstraction, they've never even said exploring it, because it's more like you're telling me that now I have something that I can upgrade anytime. Now there's a catch there. It's not really upgrade anytime, like I just said, but then you have something that I can upgrade anytime. And anytime I just want to add a new feature, I can upgrade it, right? So now I said there's a catch. Because of these accounts interact with money, interact with real value, you can't just be upgrading your account. That's why there are companies that are building these things, and then they now have a standard so that we can have a set. For instance, agents, they have their own implementation of account abstraction. Bravos, they have their own. Even recently, Ethereum EIP 4337, they added account abstraction to the Ethereum blockchain, not natively, but on top. So there's an entry point, which I mean a contract that will allow you to do all those things, right? So basically, there are different implementations, but just know that this is upgradable. The possibilities are endless, right? Agents might come up tomorrow and say that we have added this feature to our account, contract. They come up tomorrow and say that we've added this feature that allows you to give somebody your key temporarily and collect it later. I don't know. That's just something in my head. I don't know if that, but like thinking about these things, just the fact I'm thinking about it shows you that there are possibilities. But in using EOAs, you just know that these are what we can do. And apart from those things, we can't do any other thing, right? So, like I said here, some of the potential applications of accounts. So this AA, which means account abstraction contract, is native support for multi-signatures, right? For instance, right now, if you want to do anything concerning multi-signature wallets, you would have to use a contract that has been built maybe by Gnosis, right? There's a company called Gnosis Safe. They allow you to have they allow you to have they allow you to have multi-signature wallets, and it's actually very helpful, right? But then, assuming it was account abstraction was native to the Ethereum blockchain, you wouldn't need those kind of tools, right? You'd be able to build it inbuilt into your own account, right? You don't need to go and connect to safe and all those kind of things, right? So this is just one native support for multi-signatures, right? There's something called social recovery. Now, why do you need to like why do you need to lose all your money when you lose your mnemonic? In as much as yes, we've been told that like that's how it's supposed to be, but why is it that way? Is it supposed to be that way, right? So the actual thing is that if you I don't care how much you have on your wallet, but if you lose your mnemonic, it's gone. Thinking about it, you just imagine that you lose your mnemonic today, now all your money is gone, right? So that is actually crazy. But what if there was a way using social recovery, a way to assign people that can save you in this kind in these times? Maybe you can assign like 10 people or 5 people that you say that when I lose these things, you guys will be able to make me back the owner of this contract. It's a possibility. And this is not just from my head. I've seen it other places, right? It's a possibility. But even if not for this, you would not even be able to think of this, right? This is something that will help a lot of people, because some people have lost their life savings just by losing their mnemonics, right? Or their private keys. So then another one is multi-token transaction fee payment. So I just made this thing up, but then what this means is that being able to use like any other token to pay for fees rather than just using your native token, right? Using, let's say, DAI, using USDC, using and so on and so forth, right? So basically, just opens possibilities, right? Maybe if I have one shitcoin like that that I've been on my wallet for the longest time, I just pay for fee and I forget about it, right? Right. So yeah, that I just want to think about. So I said here, with EIP 4337, Ethereum now supports this, but not natively. Like I said, there's an entry point, which is basically a contract that you would basically enter, like it will allow you to use the whole use account abstraction on Ethereum. And then Starknet supports this natively, right? The native account on Starknet is an abstract account, is a contract account, right? Yeah, another thing you can call abstract account, contract account, because they're actually contracts. But then if you're coming from the Ethereum background, you might find it a bit confusing. That's why I didn't use that from the first, because I said there are two types of accounts on Ethereum blockchain. There are EOAs, which is externally owned account, and contract accounts. But on Ethereum, contract accounts are basically just means that accounts themselves, contract themselves can actually receive, like you can actually send it to a contract now. Right? So that's the idea behind it. That's the way I see it, right? But then abstract accounts are contracts that serves as accounts to be able to perform transactions, right? So you can use this contract to sign transactions. You can assign other tokens to pay fees for you and all of those things. So lastly, let me just show you. I want to quickly show you. Our time is past tense, but pardon me. I'll just quickly show you. So this is an account. This is the agent implementation of an abstract account, right? So this is it, right? So this is an account. So you have a couple of functions. I know you might not understand, is no problem. I just want to show you that there's a contract. So basically, if you create an account on Agent, if you download your Agent wallet and deploy your account, this is what is running. So you are not just using your private key and all those kind of things. Yes, under the hood, there's a private key, don't get me wrong, but these things that this will be what will be running transactions for you, not your main, like if you sign a transaction, what will be showing is this account address, not the account or the address tied to your private key. So let's quickly go over this. There's a validate function, there is a execute function, there is a validate declare. You don't need to know what it means. I just want to show you how the function it have just one account, rather than just having something to sign transactions. You're having a contract that have different things inside of it. It's valid signature. It is generic. So this initialize, which is you help you create them. Now, see something very interesting. Upgrade, right? So first, like I said, you can upgrade your contract, right? You can increase it to something different. You can add more logic to it and upgrade it, right? So you can add more logic to it and upgrade it, right? And then the other thing is change signer. Just imagine you can change your signer you can change Guardian, you can change, and all those kind of things, right? So these are like a lot of things you can do, which you would normally not be able to do using your normal EOAs, right? So this is like a lot, right? This is really good, right? So we have come to the end. So quickly, when I share the slide, you can just read up on all this. These things are very interesting articles that would really help you understand these things more. And then thank you very much for listening. This is my Twitter, my LinkedIn, and my personal website. You can go and check it out and maybe know more about me. Yeah, thank you very much. And please, now you can, I think, yeah, you can unmute yourself and ask questions. I would really appreciate that. Okay. If you don't have questions, just share with me something that you really like something you understood, right? Anybody, just share with me something you understood.
Yeah, hello. God's power. So
yeah, I can hear you.
I
Yeah,
was
go ahead,
having a
please.
bit of a hard time to understand Starknet and all the other stuff you're talking about, but at least I understood the rollups, the different types of rollups, the optimism, and the other one that requires validation. So that was
Great.
something I understood perfectly now. So I didn't know ZK rollups have different types. Like there are so many types. I just assumed it's one thing, but now at least I know much about it. So I'm looking forward to understand stacks. Yeah, on the dev side, I'm an aspiring dev, so I hope you will help us understand more.
Yeah, sure.
Apart from the theory.
Yeah,
Part.
sure. Yeah, thank you for sharing. Quickly, can you just maybe ask any question you have about Stack? Just ask if you feel like, just ask, maybe you can answer it quickly before someone else speaks.
Okay, about the EIP protocol, the one you're talking about, could you elaborate what you meant by, I'm not exactly sure of what you said, but you said there's an entry point. Yeah, entry point.
Yeah.
And then Stacks is involved. Is Stacks the entry point to that EIP or what was happening there?
Good. I like, very good question, because I found out that, like, yeah, I thought some people would not understand that, which is, thank you for asking that question. So now, when I started explaining account abstraction, I said that validity proofs, zero knowledge proofs are very different from account abstraction. Account abstraction is a very different topic on its own, a different concept on its own. It doesn't have anything directly to do with proving stuff, right? But now, when I talk about entry point, I said that natively, so which is natively, account abstraction is not built into the Ethereum protocol. So under the hood, you don't have account abstraction on Ethereum. You have normal accounts, EOAs, normal accounts that used to collect it. That's all, right? Now, they were asking, how do we bring in account abstraction without altering the protocol? You understand? Because most of the things you see on Ethereum today are built on top of the protocol. They're not built inbuilt, right? It's more like you have a computer, you can install many things on it, but you're not changing in infrastructure, you're not changing the architecture of the computer, right? So that's what they are trying to say. So basically they built something to allow account abstraction on Ethereum without altering the protocol itself. Now, when I mean an entry point, it means that they are doing this using a smart contract, which that is what most people use, right? In fact, every application built on Ethereum, even L2s are contracts on the blockchain. Uniswap is a contract. Tokens, they are contracts. In fact, the only thing native that most people know, the other things are native to the Ethereum blockchain, but the only thing native is it. There are other things under the hood, don't get me wrong. But the only thing native that we all know about is it. Most of the things we know about were built on top of it. From DEXs to NFT marketplaces to ERC tokens, shitcoins, every single thing you know about was built on top of it, right? So it's built to be a world computer, so to say, right? So basically, when I said entry point, I'm saying that this is its own contract. Its own contract. So they built an entry point, a way to use this. So because of it's something that most people use, they need to be a way for people to interact with it. So basically, that's an entry point, right? A way for people to use account abstraction on Ethereum, maybe to create your own abstraction contract, maybe to send transactions and all those kind of things. So that's what I meant by entry point, right? And also this EIP, it means Ethereum request for comment. Sorry, Ethereum improvement proposal. So it's just basically you have an idea, you propose it, people start reviewing it, you start going through different stages, and all of it. So and after a while, they approve it. So that's why it has EIP is Ethereum improvement proposal. Basically, from what I understand, is probably the 4337 Ethereum improvement proposal. So people are proposing things, both like even this one is Vitaly Buterin was part of people that proposed it. And then these things go through different stages, they discuss about it, and before you know it, they implement it, right? So that's what this thing means. So when I said entry point, I meant a way for people to use this account abstraction on Ethereum. So does that help?
Yes.
Cool. Yeah, so I know the time is fast spent. Does anybody have Paul, do I actually have more time? Or am I the one? Because nobody's talking about the time. Maybe I'm the one.
No, no, you can attend to questions like
okay.
definitely.
Yeah. Please, if you have questions, drop it on the chat or just speak. Okay. I've noticed occasionally that to upgrade agents and bravos, when we fail to upgrade, does it mean we lose access to our funds and we discontinue into the future and upgrade our contract every now and then? Yeah, it's actually a thing. So basically, what I understand from these things is that when you're at the building stage, you tend to make modifications, and it's for the better, it's for the best, right? In as much as it might not be convenient, but yes, they are doing a lot of upgrades. Even on Starknet, they are doing a lot of upgrade, right? But there's something called a stable release or a stable version. The time will reach whereby every update they make, you might not even notice it, right? Or you might not, but because of it's an abstract account, yes, you might have to upgrade, but then it might not be major. You understand? It might not be major or even make it. But I don't think, I know there's something that came out the other time that said you might lose your funds, but then yes, if maybe you are far back, right? Maybe you are like your version is outdated, yes, you might lose your funds. But right now, I think if you upgrade as they go, because I think they give time to upgrade, you will not lose your funds, right? And also, like I said, the reason is because a lot of things are changing, a lot of things are improving just for the better of the ecosystem. But yeah, for now, you might see a lot of that coming up, but a time will reach whereby you will not see that anymore, and most things you see are just very little changes. Yeah. So I think our time is fast spent, and let me just pass it over to Paul. Thank you very much, guys. Yeah.
Yeah, thank you, man. That was actually a very good class, very good section. And yeah, and thank you all for attending once again. And we'll have the last one next 2 weeks as well. And within the week, I'm going to send out the assessments. Also try to attend to the first one we sent out. Some people have actually sent in their answers as well, but a lot of people have not actually done that. So you can try and attend to the assessments before we send in the one for this week. Okay, so yeah. So since we are done, I guess we call it a night, right?
Yes.
So-
Oh, quick reminder that the next class is on 27th, right? So please let us remember the next class is on 27th. We are so thankful that you're here, all guys. Also engage on the Telegram group, ask questions, and you can reach out to anyone. If you post your question, it would be will be able to be responded to. And also, if you want to dig deeper, you can get the slides and this recorded video also via the group. If you haven't registered, please register so that you can get the notification. So thank you so much, and you guys will be the next stackers after a month, I think. So thanks.
Yeah. Great, thanks, guys. Good night.
Good night. Thanks, Eze. It was a nice work.
Yeah.
All right, guys.
Thank you.
Yeah.